The AI boom is completely changing our world. But behind all these incredible new tools, there's a hidden cost, a massive one: power. The amount of energy AI needs is pushing our entire infrastructure right to the breaking point. And it's sparking a technological revolution that's become, believe it or not, a national mission.
Okay, so to really get where this is all going, we first have to understand the sheer scale of the problem. The artificial intelligence we're building, well, it has an absolutely insatiable appetite for electricity.
Take a look at this number. By 2030, data centers, and this is mostly because of AI, are projected to eat up a staggering 21% of the entire global energy supply. And no, that's not some wild guess. That's a forecast from the International Energy Agency. It's a massive, massive jump from where we are today.
An expert from MIT really nails it with this quote. The very thing that makes AI so amazing, its progress, is what's driving this crisis. As these models get more and more complex, moving from simple text to processing real-time video, they just devour exponentially more power.
And here's the really alarming part. Look at where we're starting from. Before this whole AI explosion, data centers already used as much energy as the entire airline industry. Think about that for a second. Now, AI is strapping a rocket to that consumption and sending it nearly straight up. So this incredible demand is pushing our infrastructure right to the edge. And the answer isn't just, build more power plants. It's forcing us to completely reinvent the digital factories, the data centers, that power our modern world. The data centers we built even 10 years ago just can't handle this. They were designed for a totally different internet, running on 12-volt systems with good old-fashioned air cooling. Today's AI workloads are so intense, they would literally melt down in that kind of environment. The new standard is a complete top-to-bottom redesign. Now here's where it gets really interesting. Where is the solution coming from? Of all places, the electric vehicle industry. Tech giants are borrowing directly from the EV playbook, making this huge leap from 12-volt to 400-volt power systems. And to deal with all that heat, liquid cooling isn't just a nice-to-have anymore, it's an absolute necessity. And this really shows that solving the energy problem is a multi-layered challenge. You can think of it like a multiplication problem. You need efficiency in the IT gear itself, the chips, the servers, and you have to multiply that by the efficiency of the building that houses them, from the power connection all the way down to the cooling pipes. One without the other just doesn't work. But this massive jump in power and cooling is only possible because of a quiet but incredibly profound revolution happening at the most fundamental level: the actual materials we use to make semiconductors. The key technology here is something called a wide bandgap semiconductor. Okay, so think of the bandgap as a material's ability to handle electrical pressure. Silicon has a pretty narrow gap. These new materials have a much, much wider one, which lets them handle far more extreme voltages and temperatures, exactly what these new AI data centers are demanding. And this table just lays out the massive performance difference. Just look at the bandgap, that's voltage handling, and the thermal conductivity, which is crucial for getting rid of heat. In pretty much every critical category, materials like silicon carbide, or SiC, and gallium nitride, GaN, leave old-school silicon completely in the dust.
So what does this mean in the real world? Well, the advantages are enormous. These materials let us build power systems that switch faster with less energy wasted as heat. They work perfectly at much higher temperatures, and you can pack them into much, much smaller components. It means more power, less waste, and a smaller footprint.
And you've got to understand, this revolution goes way beyond just AI. These advanced semiconductors are the foundational building blocks for a whole host of next-gen tech. We're talking more efficient electric vehicles, a smarter and more resilient energy grid, the whole shebit. In fact, this technological shift is so critical that it's moved way beyond just corporate R&D. It's now at the very heart of a major strategic initiative from the US government. It's an initiative called the Genesis Mission. And according to documents from the White House, this is a national effort to build the world's most powerful platform for science, bringing together supercomputers, AI, and huge data sets, all to accelerate discovery. And the mission has 3 crystal-clear goals. First, achieve American energy dominance, both by modernizing the grid and through things like fusion research. Second, advance fundamental science. And third, ensure national security. Everything from stockpile reliability to developing new defense-ready materials. The official order says that the goal is nothing less than furthering America's technological dominance and its global leadership. This is a huge signal. It means this energy and computing revolution is now seen as a matter of national importance, on par with historic efforts like the Manhattan Project.
But, and there's always a but, this ambitious plan to fuse technology and national strategy is not a guaranteed win. It's facing some pretty significant hurdles and some very legitimate skepticism.
For one, on the technology side, those revolutionary semiconductor materials, they're still expensive and really difficult to manufacture at scale. And the global supply chains you'd need for a full industrial shift are still being built out, which could create some serious bottlenecks. And then there's a broader critique. Some folks are worried that this massive top-down push is just going to lead to a colossal waste of resources, that will pour all this energy into AI projects that end up failing, while other really important areas of science get left behind.
So that leaves us with the ultimate question, right? We are literally rewiring our world to power artificial intelligence. Will this new grid, built on these revolutionary materials and driven by national ambition, truly unlock a new age of discovery? Or are we building the infrastructure for what might be the most expensive gamble in the history of science? The answer to that is still being written.